Hello, everyone. Welcome to the seminar today. We are very happy to have Taige Wang from Berkeley to speak today. Taige is currently a PhD student who is about to finish his PhD study this summer and then become a postdoc at Harvard. During the PhD study of Tiger, he has done many interesting works. I think one distinctive features of his research is to apply the numerical approach to address many problems that are conceptually interesting and experimentally relevant. In particular, Tiger has done a lot of work on marine materials. I think the talk today is either directly or indirectly related to that. Tiger, please.
Yeah, let's put it more inspired. Okay. Thanks, Liu Jing, for the invitation. It's my pleasure to be here. And it's great to see all my friends on Zoom. Um, it's it's my pleasure to share our recent work on this transition theory out of topological order, which I think is quite more inspired, but it distinguishes itself from array. Okay. So let me say a little bit about the motivation. Okay, the motivation is not moray, but this generic pursuit of beyond Landau transitions for us theorists. So Landau really solves many problems. Like Landau solves most metals. You have the Fermi liquid theory. Landau solves most phase transitions. You have this Ginsburg-Landau theory, this symmetry breaking transitions. Most things in our world, in our universe, like the vapor to water transition, is all described within Landau. So it's actually very hard, but also very interesting to study those examples beyond it. I know a few categories, so let me just summarize here. I think it might not be comprehensive, but it's fun to talk about. The first category I know of, which is beyond Landau, is disorder-driven transition. Okay, a famous transition is the Nukes 1 to Nukes 2 transition. When the temperature is not that low and disorder is not that low, you do not see the fraction quantum Hall state. Instead, you always see a transition from Nukes 1 integer quantum Hall to Nukes 2. And there has been debate for decades of how the transition is realized. And now we realize you have puddles of nukes 1 and 2. And once the domains are connected and you go through the so-called percolation transition, we can have precise prediction on all the exponents at this transition. You can also have this localization transition going from a metal to Anderson insulator. So in both these two cases, it's difficult to transcribe as a symmetry breaking. You might be able to do it somehow by the replica trick, but just if I give you a disordered metal, it's hard to write down autoparameter that you can write down Ginsburg-Landau theory. So this is one category I know of. And there's another category that attracts more attention recently. So there are certain phase transitions between two phases that are within Landau. Okay, let's say a new order and a VB order. But the critical point is certainly beyond Landau, like the famous DQCP story. So people, including Liang and Sento, Ashwin, lots of collaborators, developed this idea of DQCP. At the critical point, you have this emergent SO5 symmetry that is beyond Landau. And also another example will be the symmetric mass generation. People discuss how to obtain a transition from a metal to a featureless insulator. So the two sides are perfectly well within Landau, but there are no good autoparameters that distinguish the two and allows you to write down Ginsburg-Landau theory. But the category I'm most, at least I worked on the most, are transitions between phases beyond Landau. Okay, so if you have a transition from, let's say, bosonic Laughlin state to a bosonic superfluid, there's no way you can get a transition that's within Landau because there's no Landau description of the Laughlin state in the first place. Okay, so this will be star of today's talk. Okay, I spent quite some time on different transitions within this category, but I think we understand this Laughlin to superfluid transition the best.
Um,
And
I got uh, so just the simplest transition between metal and a band insulator by tuning the
yeah,
particle potential is also maybe a simpler example of transition beyond Landau, right?
that's right. That's right. But that only happens at commensurate filling. So that's why people didn't discuss it too much.
Mhm.
Yeah. But this also somehow applies to SMG. For SMG, you have some commensuration conditions as well. So depends on how you view SMG is another question. Um, but going back to this Landau to superfluid transition, as Liu Jing said, it's this entire category was more or less Moray or 2D materials inspired. Okay? And there's good reason why people spend more time thinking about DQCP than these transitions out of Laughlin state back in the days. Okay, so there's just no experimental realization of transitions between Laughlin state with anything else that's non-topological. So it's not until recently we have seen all these FCI states or the analog of fraction quantum Hall states in 2D materials, and they do transition into all kind of phases like charge density wave, etc. Because you have so much tunability in a 2D material, which you don't have in lambda levels. Okay? So this just opens up all the experimental possibilities. For example, people believe that they have seen transitions between the Laughlin state to a charge density wave in a twisted TMD material. And people believe they have seen composite Fermi liquid to Fermi liquid transition in Römer graphene. And also, Xiaogan is pretty confident that he saw transitions between the daughter state of the Fabian state to the Jan sequence in bilayer graphene. Sorry, not truly bilayer graphene, but bilayer quantum Hall. Okay, I think in his case, bilayer of gallium arsenide. So the later three are indeed more or less observed in the experiment, which inspired this study of this entire category. But the star of the today, the Laughlin to superfluid transitions, has not been observed yet. So I think I can call it one of the motivation to why we want to study it numerically. Okay. So within this whole family of transitions, let me just talk about Laughlin to superfluid transition today. So maybe the first thing you want to do is to find out a microscopic model that can realize this transition. Let me write down the following Hamiltonian. So this is within the lowest lambda level of bosons. And the interaction I consider is a contact interaction. And it is well known that if you dope to nukes to 1/2 of the lowest lambda level, this contact interaction, you project the contact interaction to the lowest lambda level, it becomes the parent Hamiltonian of the nukes 1/2 Laughlin state, bosonic Laughlin state. Okay. Um, and the second part I add is the periodic potential. So due to the special magnetic algebra in lambda levels, all I need to do is to add a periodic potential. So it couples to the density operator rho r, and it's periodic in the sense that I have a lattice constant A and the reciprocal lattice constant Gj. Okay. So the transition I want to study is by tuning this periodic potential Vm. And due to the magnetic algebra, the strength of the periodic potential simply translates into the bandwidth of this lowest lambda level. So the easiest way to see it is that the density operator is also eigen in the momentum space. So if you write on rho k, it's actually eigen under this periodic potential. And you'll see that it obtains a dispersion, which is precisely cosine k dot a, where a is the reciprocal lattice, where a is the lattice vector of this periodic potential. Um, so it's well known that the contact interaction is the parent Hamiltonian of the Laughlin state. You will have an exact zero mode. The Laughlin wave function will be an exact zero mode of this Hamiltonian. So we know when we turn off Vm, when the periodic potential is turned off, we obtain a bosonic news to 1/2 Laughlin state. And if I turn on the periodic potential, if I go to very large Vm, but still smaller than the cyclotron gap, I can neglect the interaction. Then, due to the magnetic algebra, you can solve for the band structure. It simply flows in this way. Okay? Um, because the rho essentially because rho k is eigen under the translation operator. So in particular, I have been considering a square lattice for now with a 2 pi flux per unit cell, as we will see why it's the case. It will give me such a simple dispersion for, let's say, that you usually see on hopping model of a square lattice. Okay, so when interaction is small, which means VM is very large, we also know that we're in the limit where you will get a boson superfluid because it's boson and has a minimum at the gamma point, it will inevitably condense. Okay. So we understand the two limits fairly well, the limit where VM is zero and the limit of VM is infinity. Okay. The interesting thing you want to ask is what happens in between. So is there a continuous transition in between, or is there intermediate phase? And at that point, you cannot do perturbation on either side, so you have to rely on some numerics. But before I proceed to the numerics, maybe I should pause and see if people have questions on this microscopic model. Okay, numerics. So the numerics we did is set up on infinite cylinder. Okay, so we just consider lowest lambda level bosons on infinite cylinder, and then we add a periodic potential as promised. So this is we're doing IBMRG, so it's not a truly 2D algorithm. You always consider a cylinder version of it. So you wrap your lambda level around this cylinder, and the wave functions, such as famous lambda wave functions, is not modified. And we can go to at most Ly equals 12A, so 12 unit cells around the cylinder. And now I'm showing the result of Ly equals to 8A, which probably converges the best. So as I tune the periodic potential Vm, on one side, if I tune Vm to 0, it's expect to a Laughlin state, as I discussed. But you tune Vm to be very large, you expect a superfluid. So let's first check we get the two phases right in numerics. The characteristic feature of a Laughlin state will be the entanglement spectrum. So based on the Li-Hao-Deng conjecture, and now we have a set of proof from Xiaoliang and more work on Ziyang. But the understanding is that if you have a cylinder, you cut it in two halves, and this will allow you to compute the so-called entanglement spectrum, which basically means you want to you usually just consider about the entanglement entropy, which is like the sum of P log P. But if you put P out and label it with a Ky momentum, you can write down the entanglement spectrum. So maybe let me write it more clearly and a bit more in the MPS language. So basically, for any state psi, you can do a Chorder decomposition. And we call the lambda alpha square will be oops. It asked me if I'm speaking English. I hope it agrees. E to the minus epsilon alpha. So epsilon alpha will be the entanglement energy. And you can resolve everything in momentum. So you can have a momentum label in all of these, meaning how much momentum there is within the left and right sector. Then everything here can be labeled as momentum. And then you can plot this epsilon alpha k, which is precisely what I plot here. So from the Li-Hao-Deng conjecture,
Is this momentum in the y direction?
yes, this is in the y direction. So based on the Li-Hao-Deng conjecture, we know this entanglement spectrum should have, it won't be exactly identical, but at least have the same counting as the edge CFT. Okay, so it's when you compute the entanglement spectrum, it more or less tells you what if you really put a physical boundary and what's the spectrum of the edge CFT. So if you look at the counting, it's a famous 1, 1, 2, 3, 5. Maybe you can read 7 here. So that's a characteristic entanglement spectrum for a Laughlin state or for a topological order with a chiral boson mode. Because if you count the excitation spectrum of a single chiral boson mode, you'll find this counting. Okay, so this entanglement spectrum on the left side just clearly tells you that within this entire phase, it's a Laughlin state. And the characteristics for the superfluid states will be the boson-boson correlation function. So it's not like usual Ising transition, Ising ferromagnet. Since we're doing a 1D DMRG, so it's intrinsically 1D, you do not expect spontaneous U1 symmetry breaking. Okay, we are working with the infinite cylinder, so the finite size argument didn't save us. So instead of just allow it to spontaneously break the U1 symmetry and measure the U1 symmetry breaking, usually you can measure B, the expectation of B. But in this type of 1D calculation, we always preserve the charge or particle number U1 symmetry, but instead you compute the BB correlation function. So if it has this tendency to spontaneous symmetry breaking, in 1D's manifestation is that the BB correlation function will give you an algebraic order. Okay, so a decay in parallel with the distance between two boson operators. If you want to be incredibly rigorous, you also care about this exponent eta because it will compete with other orders. But in this case, if you compute eta, eta is very small, meaning this ordering tendency is strongest among other channels. So this is when I plot the BB correlation function for this superfluid site. Okay, the x-axis is the distance between two boson operators, and this is a log-log plot. So this linear decay is a clear indication of this algebraic order. And you can cross-check if you look at the BB correlation function in the Laughlin state. I still plot it in log-log scale, but if you plot it in a linear scale or log linear scale, you will see a nice exponential decay of the boson-boson correlation function. And also in the superfluid, people has a good understanding like this a detached, almost flat band of the entanglement spectrum is a characteristic feature of a superfluid. Max and Tehran has been quite some time to understand these features. So from these plots, I hope I have convinced you that at least the two sides are what we expected. When VM is very small, you get a Laughlin state, but when VM is very large, you get superfluid. And the interesting thing is what happened in between. So if I just plot the correlation function, it diverges because the superfluid phase is a gapless state. So usual detection or usual characteristic of the phase transition no longer applies. If you just simply plot the correlation function, it's gaps on one side, on the Laughlin side, so it's finite, but it's going to be gapless in the superfluid, which is a gapless phase. But as I will show later, it's possible to define correlation function at certain momentums. And this is a momentum that contains the mode that drives transition. If you only look at this sector, this particular endpoint momentum sector, you will see the expected divergence of correlation length at the critical point. I think depend on how you read the left scale. Let me just erase this. Um, sorry. Oh, sorry. I'm still. If you read the scale, the correlation length at 10,000 bond dimension reaches about 5, which is already fairly large. Given we're on a finite system, it can never truly diverge. So,
Tiger. So
yes.
Suppose you use connected correlation function to detect the phase transition and see whether there's a divergence correlation length. Uh, why does it not work?
Oh, it's genetically very hard to obtain the correlation length from the correlation functions. So yeah, maybe let me say a little bit about how I obtain these correlation lengths in
Well,
practice.
I mean, if I use this is DMRG simulation, if I use the eigenvalues of the transfer matrix to obtain the correlation length, that correlation length corresponds to the correlation function, the connected correlation function.
That's right. That's precisely
And
being plotted here, the blue curves.
yeah, then in the superfluid, the connected correlation function is also supposed to be small, right? Unless you
Um,
are in the GSC state, but I don't think you will be in the GSC state.
no, if I catch through the ghost mode, then it's gapless.
Yeah, it's gapless, but the connected correlation length should still be small, right? Let's imagine the ground state. Then instead of thinking of a superfluid, let's think of an XY magnet,
Hmm.
which also spontaneously breaks the U1 symmetry.
Yeah. Okay.
Then one ground state is just a state where all spins are pointing in one direction, where the connected correlation function is just zero.
Yeah, perfect. So the complication comes in because you can never have spontaneous symmetry breaking of U1 symmetry in 1D.
Uh-huh.
So in practice, the connected part, um, so if you're basically suggesting I can compute something like this, right?
Yeah.
But this part will be identically zero because we preserve the U1 symmetry. We do not allow it to spontaneously break.
Mhm.
Even if you allow it to spontaneously break, it will not break because it's in
Yeah.
1D.
Yeah. Another question is in the correlation function in the superfluid, there's some oscillation. If I look at the period of this oscillation, does it exactly match the one predicted by the KF coming from half filling?
Oh, it's not from KF actually. It's from. Oh, you can also say it's come from KF. But in this case, you have a real space interpretation. It's really because this is plotted in real space, and this x equal to zero, b zero, is at some point. I don't remember. I think it's probably here. Then you have oscillation within the unit cell. So it's really oscillation within the unit cell. It
Oh,
goes back if I at here. So it's not a pair density waveform. It's not a finite momentum superfluid. It's
uh-huh.
also high frequency. It's high momentum oscillation within the unit cell.
But in this quasi 1D geometry, if the state is a Lagrange liquid, generically all those correlation functions will have oscillations coming from KF.
That's right.
So do
That's
you
right.
see it here?
Yeah, I'm not familiar with bosonic versions of of Loughlin of Lagrange liquid. Um, yeah, how should I think about it if it's boson?
It's almost the same as fermion, right? Just in the operator spectrum, we remove some local fermionic operators. The
I
when
also
we write down the fields, there's still the theta field and the phi field, but some of the exponential combinations of theta and phi will be fermionic. We remove them from the local operator spectrum.
Mhm. But how should I understand KF for bosons?
It's also the same. For example, let me view it as a 1D system with some partial fading. You know, there will be some fading constraint, and there should be some anomaly matching condition that requires the translation symmetry to act on some non-trivial way, meaning there must be some non-trivial KF.
Yeah, I
Then
see.
when we relate microscopic operators with the field theory operators in the Lagrange liquid, there will be some KF.
Yeah,
All these can be found in Spear's book, chapter 19, I think.
you are very familiar. I see. Let me think about it. I never understand the bosonic case of Lagrange liquid. in this particular plot, oscillation is just from this unit cell oscillations. But yeah, I should think about that.
Mhm. Yeah.
Yeah. So any other
May I cut
question?
in?
Yes.
Uh, uh, I think just a comment. So, are we actually dealing with the hardcore boson here? Because it's not a hardcore boson you can condense in other way.
Oh, it's
Like, can
not.
I think of the bosonic? It's not hardcore, but you have a contact interaction, right?
Yeah. Okay. In that sense, yeah. But
So that's why you can apply
no
laundry
problem.
liquid.
Yeah, because oops, I'm still drawing. So it's not a hard constraint. It's a energetic constraint. So when VM is large, then it's not a hardcore boson.
Mm-hmm. I see.
Yeah, if
Yeah,
VM is
okay. I
zero, you
see.
can interpret it as a hardcore boson. I agree.
Yeah, I'm just thinking about like if the boson actually condense at one momentum, maybe there's no KF definition. So that's something I'm also not sure. Yeah, for the
Yeah,
laundry liquid description.
yeah, I know
Okay.
little about the bosonic Lagrange liquid. I don't understand what the boson superfluid means in the language of a boson Lagrange liquid. I have to admit. Yeah, but let me pause here again and see if people have questions about the diagnosis of these two phases. I think that's a starting point of this entire study. We have to agree upon that the phases is Laughlin and superfluid. Okay, great. Now we can talk about the transition. So when we write up the paper, I think Ziyang told us, yeah, now it's already published. Their amazing work of doing a similar study on a lattice model. They also seem to have seen a continuous transition from just scaling collapse. Um, but okay, there are complications why we don't do scaling collapse and etc. But just to say that um, at least now we, from very different models, have agreed upon that there could be a continuous transition. Okay, so from our numerics on this lambda level problem, it seems clear that it's second order or continuous transition. If you look at there are many things you can look at. You can look at the energy of the superfluid autoparameter. It doesn't have a kink, but it grows continuously in VM. And if you look at the correlation length, it seems to peak as a critical point. So these are characteristics of a continuous second order transition. Okay? If it's a first order transition, it will usually be like this. So the two phases simply have a different correlation length and it jumps across the transition. Okay. So now the interesting question is, what is the nature of this critical point or this continuous transition? If it's first order, there's no studies you can do further upon. But if it's continuous, there's a lot we can say as theorists. So this transition, actually, Mason and John, 10 years back, has proposed a few theory that could describe such a transition. So it relies on doing a parton construction of your bosons. So just fractionize your bosons into two fermionic partons, F1, F2. So since now our bosons at nukes 1/2 filling, it just means our fermions, the fermionic partons, will be at integer filling. So maybe it's more clear if I say it the following way. This B bosons will each boson B will experience two flux, and these two flux can be split. Okay, so this filling is arbitrary, but one way to split it or one way to write down the mean field answers is to assign one flux to F1 and one flux to F2. So for each fermionic parton F, it sees one flux per particle. So in other words, it will be at nuke to 1. So this is just a way to say there's a simple, this is actually identical. I will show you later. But this just gives you the Laughlin state. The integer quantum Hall of the bosonic partons F, they are both in nuke to 1 integer quantum Hall, as discussed here. They will give you a Laughlin state. And the possibility of transition into a superfluid state in a continuous way is for one of the partons, F2, to form a CX2 -1 Chen band. Okay. Now, upon integrating out F1, the resulting field theory you get will be for the Laughlin state if the Chen number is 1 for the fermionic parton F2. But if it's CX2 -1, it will give you a superfluid. So this is the incredible thing about the entire construction. When I think about superfluid, I think it's very hard to describe. You have to let bosons to condense. But it's very different in the parton language. In the parton language, both partons are gapped. Okay? So you don't need gapless degree of freedom from the partons. The gapless degree of freedom actually comes from the dynamic gauge field. So the only thing you need for a superfluid is for F1 and F2 to have a CX2 1 and -1 Chen band, as I will elaborate later. So, but at least the Laughlin side is identical to flux attachment. Usually we say to get the Laughlin state, you attach one flux to the bosons to form a composite fermion, and that composite fermion experience unit flux. So it will form an integer quantum Hall state. And that's precisely what happened to the F2 fermionic parton. So doing this parton construction and put F1 in the integer quantum Hall and then integrate out F1 precisely did the flux attachment. Or you can see this is a way to implement the flux attachment. The Chen-Simons term comes from integrating out nuke to 1 integer quantum Hall of F1. Okay, so it's the response of F1. And the coupling between F2 and the dynamic gauge field A mu is from this parton construction because there's a dynamic gauge field A mu between the U1 rotations of F1 and F2.
May I ask a question, Taige? Yeah, according to your Lagrangian, I didn't see the tuning parameter to achieve the transition between the lovely and the superfluid.
Very
Could you
good.
please tell me that?
Yes. So it has to happen in the Lagrangian of F1.
Oh, good.
So now this version I write down has already integrated out F1, assuming it's in a nuke to 1 integer quantum Hall state.
Okay, sure. So your Lagrangian is already on the critical point between the different phases.
Oh, sorry. This is a Lagrangian deep in the Laughlin state.
Oh, yeah, that makes sense.
Yeah.
Thank you.
Yeah, I was just trying to explain how to understand this parton construction. It might seem alien to people, but it's nothing but the flux attachment approach, the composite fermion approach. It's deep in the Laughlin state. And oh, I see. Okay. I think I wrote it in a slightly confusing way. Yes, sorry about that. I should really, yeah, okay, good. Um, yeah, nobody pointed it out when I give these talks elsewhere. Um, but indeed, so in my mind, the logic should be I can tune which state F1 resides in, at least from this equation. Okay, later I will use F2. So maybe the better change I should make is to do this. I don't remember which version I used later, but the point is the Chen number of one of the fermionic partons has to flip, and that changes the Lagrangian of the other fermionic parton upon integrating out this fermionic parton. It's crucial to realize what enables this transition. So if you are in the lambda level, there's no way you can get a superfluid. So this is really because if you are in a lambda level, the Hall conductance or the Chen number is locked to your filling. Okay? So you can redistribute your flux any way you want, but F2 always experience unit flux throughout this transition. It is the band structure that allows it to have a Chen number different from the filling. Okay? Um, so this is why this has been being really studied a lot because you have to add at least within this formulation, this microscopic model, you have to add a periodic potential to drive this transition. There's no way to drive such transition by tuning, for example, the precise form of the interaction or different lambda levels. If you do not break the translation symmetry, the Chen number of the fermionic partons cannot change. This actually on the other hand, this corresponds to what you expect from superfluids. If there's no if there's no periodic potential, the lambda level is protected to be exactly flat. And in that limit, you just cannot have any dispersion or kinetic energy. Therefore, you will not want to favor a superfluid. Okay. 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 Eventually, I choose to integrate out F2. So in the previous slide, it should also be integrated out F2 and right now Lagrange for F1. So the question is, upon integrate out F2, depending on the Chen number of F2, I get different response terms at the end. So let me just write out the final response. So I further integrate out F1 as well. So if C equals to 1 for F2, you will eventually get 2 over 4 pi ADA. And if you integrate out A, you will get 1 over 4 pi, the big A, d big A. So it gives you the ground state degeneracy 2 from this self-Chern-Simons term of the dynamic gauge field, and also this quantized Hall conductance from the background gauge field, the background Chern-Simons term. So that's the state we usually understand. But generically, you can ask what happens if C is different. Now you have a band structure. So when CX to 0, you'll find that you just get a 1 over 4 pi ADA. So it will be a charge density wave. But most interestingly, if you have Chen number equals to -1, you no longer have this self-Chern-Simons term for the dynamic gauge field. So it really means the theory no longer has to be gapped. Okay, so for CX to 1 or 0, the theory has to be a gap state because you have this Chern-Simons term that opens up a gap. But if CX to -1, you have to worry about the Maxwell terms of the dynamic gauge field and the background gauge field. If you do some manipulation, it will give you the familiar action for superfluid, which I think is pretty cool. So the idea is that if you allow these fermionic partons to cancel out the self-Chern-Simons term, you can obtain a gapless state. And usually when you obtain a gapless state, it's very likely to be a superfluid superconductor. Yeah, Liu Jing, I saw you want to say something.
Oh, I think I have a very basic confusion. Is sigma xy equal to 1 or 2 in this Laplace state?
Oh, yes, sorry, this is a typo. Yeah. Other people point out this typo previously, but I forgot to change my slide. Yes, if you integrate out little a, because you have this 2 in the denominator, you will get 1 over 8 pi ADA. Sorry about that. Okay, so now we are able to formulate this transition between a fractional quantum Hall state, a charge density wave, a model insulator, and the superfluid by a Chen number transition of the F2 parton. So if CX to 1, it's a Laughlin state. If CX to 0, it's a mild insulator. And if CX to -1, it will give you a superfluid. So this gives you a framework to describe continuous transitions between these 3 phases by the Chen number changing transition of the parton F2. Okay. So this is what we want, Liu Jing. This is a Lagrangian that describes the transition. So in order to flip the Chen number of the F2, the easiest way is to write down Dirac fermions, and then the mass term of the Dirac fermion controls the Chen number of the band. And it's not just QED, but a Chern-Simons QED because you always have this 1 over 4 pi ADA, the Chern-Simons term, throughout this transition. So I hope this slide established the basic framework of this transition. It's just described by a QED transition of the F2 partons, when you flip the mass term of the F2 Dirac fermion. Yeah. So if you look at how much, because the Chen number has to change by 2 from the fraction quantum Hall state to a superfluid, so the Chen number has to change by 2, which means you really have to have 2 species of Dirac fermions, because each Dirac fermion, when the mass term flip sign, contributes to Chen number changing by 1. If you have 2 of them, then if one of them flip sign, it first goes into a mod insulator, and if the other flip sign, it goes into a superfluid. Okay, but if they flip sign at the same time, you can achieve a direct transition from fraction quantum Hall to superfluid. So it might seem as an accidental critical point from this plot because it's a single point. Generically, you might think there must be intermediate multi-insulator phase. But as I will show later, there are other constraints that forbids it and allows the direct transition. Okay, let's make our life easier by picking a specific gauge. Okay, so we're essentially looking at the band structure theory for F2, and F2 sees pi flux. So let me just consider this particular gauge a hopping model on a square lattice with a hopping t on these black bounds and minus t on these red bounds. Okay, and since I have 1 minus t here, every time you go around the unit cell, you see pi flux. So this is for F2. And within this gauge trace, this will be your band structure. Okay? You will have 4 Dirac homes in the original Brillouin zone. But essentially, since you should really work with the magnetic Brillouin zone, you will have 2 Dirac points per magnetic Brillouin zone. So these are the 2 species we will be working on, as we discussed on the previous slide. These are the 2 Dirac cones that I want them to flip sign in the mass term, so that I can realize a Chen number changing transition, and essentially this transition to a superfluid. So there are many different mass terms you can add from this depiction. You can generically have mass terms that are sigma z, so you can have mass terms, singular mass terms, just on these 2 species of Dirac fermions. But you can also have charge density waves between these different Dirac momentums. And it's very cool that at the critical point, there's an emergent SU2 symmetry. Okay, so it will be generated by the magnetic translation. So the magnetic translation does not commute because of the magnetic algebra. Basically, if you do a TX translation, it boosts TY. So the TX translation actually permutes the F22 and F21. So there's these 2 different species of the Dirac fermions of F2. So as a critical point, you expect, so the TX really boosts F2I to I plus 1. And as a critical point, you expect this magnetic translation to generate an emergent SU2 rotation among these Dirac points. So at low energy, as we discussed, I choose a particular gauge to make our life easier. But these Dirac points are not gauge invariant. you can imagine you can arbitrarily thread flux of the dynamic gauge field that will change location of these momentums. But the fermion bilinear is gauge invariant because such operation will transform F bar and F in opposite ways. And these fermion bilinear mass are precisely the charge density waves between these Dirac nodes. So they carry momentum as shown here. So they carry momentum proportion to, yeah, for the better way to say it is for momentum ky equals to pi nx, pi ny, it corresponds to this particular matrix element, a particular mass term by nx and y noted here. So, oops, sorry. So these three different CDW operators from actually form an adjoint representation of the SU2 symmetry, and the tuning parameter of the transition is the singlet mass of the SU2 symmetry. So this gives you a nice way to see why it has to be a direct transition from the fractional quantum Hall to a superfluid. Okay, so you must need something to protect the transition between the two to avoid the intermediate phase. One way is to rely on, for example, inversion symmetry. So this is what Mason and John originally proposed. But there's another nice way, which in practice could be very useful to protect this transition, which is the magnetic translation. This is why I chose it to be a 2 pi flux per unit cell for bosons and resulting pi flux for the fermion partons. And in this case, you will not go through these intermediate multi-insulator because you cannot have M1 not equal to M2. So this tuning parameter is protected by this SU2 symmetry. So this idea is also reviewed as in Xueyang and Sando's paper for twisted TMDs, etc. Okay, so this is a nice way to avoid this intermediate phase and get a direct transition. Yeah, a better way to say it is that this intermediate phase breaks the magnetic translation symmetry. Okay, so how do you verify that the low energy critical theory was indeed this QED transaminase? A very nice probe you can look at is look for this emergent symmetry. Okay? So it should be clear, I should note that the magnetic translation itself does not form or generate this entire SU2 group. Okay? It's a feature of this critical point because you have these two species of Dirac combs, and it seems nothing should forbid it from rotating into each other. So this is actually a signature of this low energy field theory. So in numerics, it's hard to, I mean, you cannot measure the gauge field, etc. But the thing you can measure is to see if you can find this emergent SU2 symmetry and see if it's coincide nicely with the adjoint mass terms. So the goal right now will be to identify these three CDW order in numerics. The nice thing is that they all carry distinct momentum. So a nice way to do it is to decompose any operator into these different momentum sectors. This would allow me to meaningfully talk about correlation length at a particular momentum. So from an operation point of view, if you look at the MPS, the transfer matrix, it naturally decomposes into different KY sectors. Okay, so that allows you to talk about correlation lengths in different KY, and the phase of the transverse matrix eigenvalue tells you about the KX, because if I write down a transfer matrix to the leading order, it's one, but there's a, I should say to the second leading order is always one. That's how we normalize it. But to the second order, or at least the one that we care about, essentially you get something like lambda alpha. This is the second largest eigenvalue. Um, and if you compute any correlation, so usually we look at the magnitude of lambda alpha because we know if we have n of them, it's to the power of n. So this is precisely so this is lambda alpha to the n's as your correlation function. Let's say b dagger b. And the two things are meaningful. One thing is the magnitude, because you expect this to be e to the minus n over c. So magnitude tells you about c, but also you have e to the I and k. So the phase of the transform matrix eigenvalues tells you which, I mean, for each one of them, for each eigenvector, tells you which kx momentum it's at. Okay, so this is how it works operationally. But conceptually, what we are doing is to decompose any local operators OR into this quick oscillation part and the slow oscillation part. And then I can meaningfully talk about in each K sector. I mean, if the slow oscillation part, I can talk about the K in the slow oscillation part. So this is what's being plotted here. I'm plotting the correlation lengths at different momentums kx and ky. So in the Laughlin state, it's clearly all very gapped. So the correlation lengths are very short, like I think 2lb. In the superfluid, it's all very large. And I should be specific that in this way, I only look at the charge neutral operators. So the charge neutral operators peaks at gamma, the correlation length, suggesting there's a ghost mode at gamma. But very interestingly, as a critical point, it's not the gamma that's most critical. It's actually these momentum at x, y, and m's. And you can check their correlation lengths, they're quite close. So there are many ways you can interpret it, but I want to interpret it as an emergent SU2 symmetry that guarantees the correlation lengths at x and y, first being most critical, and second, almost identical. Okay. It should be noted that there's no lattice symmetries that relate these 3 points. We break C4 by implementing the system on a cylinder, and there's certainly no symmetry that connects X and M. Okay, so symmetry cannot explain this accidental degeneracy about the correlation length. And you probably need SU2 symmetry to explain it.
So in terms of numbers, how close are they really are?
Let me show you the next slide.
Or maybe before that, you mentioned that there may be multiple ways to understand this. What are the other ways?
I guess I'm trying to be humble in terms of interpretation. I
Okay.
personally don't have interpretations.
Okay. Also, in this equation of OR, what is the definition of OKR?
Yeah, that's a very good point. So conceptually, you feel like this could be this separation of scales. You are thinking, basically, I guess the idea behind it is that you have this slow varying parts of the operator and quickly oscillating parts of the operator. Um, I mean, I can force you to do a Fourier transform to get OKR from it, but this operation generically is not justified if I got mixing between this quick oscillating part and slow oscillating part. Um, so I think actually the best way to understand it is from this operational meaning, because every time I only look at the most relevant part of my transform matrix. I only look at the largest eigenvalues. So this really means the modes I care about, these low energy modes, those most relevant modes, has a nice separation. So it doesn't have huge mixing between this quick oscillation part and slow oscillation part. That's the usual interpretation of this eigenvalues. Yeah, sorry, Liu Jing.
Right, thanks.
I have a question. So like for the superfluid, the largest correlation is away from the gamma point. Is it consistent with any band dispersion of your like potential or just any artifact from DMRG that prevent you from seeing a critical one at gamma? Because you're saying this is the ghost mode, I would assume it will be at zero momentum.
Yeah, that's a very good point. I never truly understand it, but I think my interpretation is that because you have this gauge, I mean, you not really have, but let me see. Yeah, I think what happened is that having a ghost mode at the momentum cut. Okay, I should remind people that I'm doing a finite cylinder, so you can see that the momentum I get is continuous in kx, but it's discrete in ky. Okay, I only have access to this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, these 10 different momentum cuts. So in practice, the system will adjust itself to avoid the most critical point, a point I will return to immediately. So a natural interpretation is that though the band minimum is at gamma, but because the band is not too dispersive, it's not too bad to have the ghost modes not at gamma. Yeah, I'm actually once confused about it. So where should I expect the ghost mode to be? It's not going to be. I think it's always going to be gamma. It doesn't care about the band dispersion of the bosons. Um, but the point is, in order to allow such a gapless mode on my momentum cut is very expensive in terms of entanglement or entropy. So DMRG just self-adjust to avoid it. So the gamma precisely cut here doesn't cut through the gapless point, but it shifts a little bit. So it gives you this funky dip. But I don't truly understand it, I should admit.
Yeah, the way it shifts is very funny. It's not shifting one way, but it's splitting to 2 points, which I don't know why. Yeah.
Oh, it just means none of these are
Mhm.
gapless. It just means you do
Okay.
something to avoid the gapless point at gamma. And this is the usual trend of your linear dispersed ghost modes.
Oh, so you're saying the only that point is avoided. So it's an artificial thing, like you said.
Yeah. I think the
I
2D
can't
limit,
take that. Yeah. Hmm.
I don't think these are the true critical points. And these are just to follow the trends, but it's just you do some the DMRG or the finite system side did some
I
searching.
see. I see. Yeah, good, good. Okay, got it.
Okay. So now it's a point to talk about how to precisely approach this critical point. If you remember from the previous plots, very first plots, I should go back to that. I don't have many slides. The correlation length is only around 4. So you do see, oops, my computer is very slow today. You do see the correlation length peaks at the transition point, but the absolute magnitude is not that large. It's limited by the precise same fact I was explaining. You will not want the momentums to cut through these direct home momentums. Okay? So this is why the correlation length will not diverge in the true ground state in any finite system. If you go to a larger system size, the correlation length will be larger, provide that you converge well enough using a much larger bond dimension. Okay, but there's a trick to get around of that. Many people attempted the trick, including Inchen and Mike, in the context of a direct spin liquid because they want to look for the direct point. But it's very challenging in their case because there are a lot of competing phases. So before you can go too far, you enter a different phase. But it turns out in my case, you don't have lots of competing phases. So this trick is very useful. Let me explain the trick. Good. So the trick is the following. Now let me thread some flux through the cylinder. Let me thread 2 pi flux. Then it's up to the system to decide how much flux it want to assign to F1, how much you want to assign to F2. Okay, it's totally arbitrary because you can change the expectation of the magnetic field from the dynamic gauge field. But if you stay within the Laughlin state, a very natural choice will be to assign pi flux to F1 and pi flux to F2, because both of them are in the nu(x)(1) integer quantum Hall state. After you thread 2 pi flux to the system, thread formula will want to give you half charge E over 2. And for these partons, if that amounts to, let me see, am I correct? It's dndb equals to 1/2. Yes, okay, it's correct. And that amounts to threading pi flux to F1 and F2. And since they are both in the integer nu(x)(1) integer quantum Hall in the Laughlin phase, they will accommodate E over 2, so precisely how much you want for the bosons. So in this way, it avoids occupying states higher, on higher lambda levels for these partons, but just adjusting the dense of state, adjusting the degeneracy of the band, of the Chen band, they can already accommodate this 2 pi flux. So that's the cheapest way to accommodate a 2 pi flux through the system, okay? Just to attribute pi flux to each parton. And just fails catastrophically in the case of the superfluid, because in that case, F2 becomes a Chen -1 band. If you thread pi flux, you want to have a charge minus E over 2. So it will create a hole in the valence band. So that causes quite some energy. But at least in the Laughlin state, we are safe. And if you want to thread pi flux for F2, it amounts to shift the momentum cuts. Okay, and it will precisely shift half of them. If you don't do this, if you look at the ground state, the K cuts will automatically choose the blue lines to maximally avoid the Dirac point. And if you precisely thread 2 pi flux, which means pi flux to F2, it will shift half of it to the orange curves and going precisely through the Dirac points. At least that's the prediction. And let's see how it works. So in the case of, I'm showing Ly to 8 and Ly to 10, they have different cuts. So this in the ground states, you want to maximally avoid the Dirac point to save energy. But upon this 2 pi flux threading, you obtain an excited state, okay, which cutting precisely through these Dirac points. And it should be noted that this excited state will precisely be a ground state in the thermodynamic limit. Okay? So the splitting between the excited state and the in the absence of a periodic potential, you certainly have zero splitting. Okay, so these two states, the ground state and excited state, are two topologically degenerate states in your setup. So that's a precisely two degenerate ground state of the nu(x)(2) 1/2 Laughlin state. Okay, and if you go to infinite system size, what happens is that the energy splitting will remain zero because topologically protected, and at the transition point, it will diverge. Okay, it's going to be a very different story on the superfluid side. But on a finite system, you always see that it remains zero for a small VM and then start to grow and start to diverge at the critical point. And now let me show you the correlation length in these two sectors. On the very first slide of the talk, I show you the blue line. Okay, it's a correlation length of the x, y, m points, and it's about 4 at the critical point. But now, if you go to this excited sector, you will see that the correlation length at these few points truly diverge. Okay, it's even much larger than the correlation length of the superfluid. So I think this is a very nice example that on a finite cylinder, you have all the compactification issues, but this trick allows you to truly probe the critical point, okay, instead of a crossover that you saw in most cases, okay. And I think this trick nicely rules out any intermediate states if you are concerned that the correlation length is not critical enough in the ground state, okay. So it just tells you that you truly have this characteristic behavior for correlation length for a continuous second order transition. And this also provides a side evidence for the Dirac combs because it's only, I think it only makes sense to me that you have these Dirac combs for F2 that will matter that much by shifting the momentum cuts of F2. So you must have something, some feature in K-space that it matters where I cut through it. Okay, so I think this is actually the way Yingchen and Mike infer the Dirac spring liquid, the Dirac comb dispersion in numerics. And if you gradually tune the flux, in numerics, it doesn't have to be 0 and 2 pi. If you gradually tune the flux, you will see that the energy goes down, and you can interpret that as the energy of the Dirac point. You can read the dispersion, the Dirac point dispersion from it. So it's not super reliable because the energy depends on a lot of things. Okay, so going back to the question for Liu Jun, so how close are they? So now I'm plotting the correlation length of the 3 points, the 3 momentums, x, y, and m. I actually cheat a little bit when I present this plot because this is actually in the excited sector where momentum cuts exactly through the 3 critical points. Though this is the expectation for a thermodynamic limit. In the ground state, the correlation length of YXM is at the same order of gamma. So it's probably in 10-20%. I don't remember which one is higher, but they're very close. But in this excited sector where I cut through these direct momentums, these points becomes very critical. I think easily goes more than 20 or so. I have this extrapolation to infinite system size showing this dark side. This originally I want to extract exponent from it, but probably that's too ambitious. I think at this point I only want to claim that the correlation lengths of these 3 momentums are quite close. If you plot all other momentums, the correlation length is about like here. So this is for all other momentums. Does that answer your question, Liu Jun?
More or less, but let's make sure what this figure means. There are 3 curves coming from data and 2 dashed curves coming from extrapolation.
That's right. So I should say these 3 curves. Okay, I have 6 curves here. So these 3 comes from, oops, sorry. So these 3 comes from extrapolation. And these 3 are the raw data at bound dimension 10,000. And within each category, there are 3 lines, the green, orange, and blue. And they correspond to momentum y, m, and x of these three momentums.
Mhm. So how bad is it if you try to obtain the exponent from this?
Oh, I think the main difficulty is to determine, okay, this turns out to be the difficulty in study the critical point of many in this many finite system setups, which is the critical point actually drifts in terms of the at different system size. So you have some transition point VM critical for thermodynamic limits, but it's different for each finite size. So the first thing you have to do is to extrapolate to find that point, and then you have to do all the scaling based on that point, but not the critical point at for each system size.
Okay.
Oh, that turns out to be quite challenging in this case. I couldn't obtain that very reliably. It's not too bad, but not that reliably. And the second complication is that I'm studying an infinite cylinder. So you cannot look at the most critical behavior because that's not okay, depending on what you want to do, but the correlation length is bounded by the system size. So you have to do scaling a regime where the correlation length does not exceed, for example, half of the cylinder circumference. Um, Otherwise, it's affected by this finite size effect because, or I should say, this anisotropy effect. Yeah.
Uh-huh.
So there are a few caveats makes me not that confident in determining the exponent. Probably I have error of plus minus zero point 0.2 or something, which is too large for exponents already, I guess.
Thanks.
Um, but Ziyang has this beautiful work extracting exponent from a lattice model. The setup slightly different. The approach he took is also slightly different. But maybe that gives you some hint. I guess, I guess more study is required to be confident of the exponent he extracted. Um, but he was able to do some sort of a scaling collapse, which gives you some exponent. Okay. I think I'm running out of time, so it's nice place to wrap up. Um, I hope I've convinced you that in this microscopic model, we have realized a continuous transition from Loughlin to a superfluid state. So that's in the half-field lambda level of bosons with a periodic potential. Okay, so that's the foundation of all these studies. And now we can go a step further to look at the nature of the transition. Um, it seems that within parton construction, you get this nice field theory that describes the transition by QED transimons. And an important prediction from that theory will be the emergent SO2 or actually SO3 symmetry that rotates between these two low energy dark homes. Okay, it's difficult to imagine the SO3 or SO2 symmetry would emerge other ways. You kind of need a two species setup to have that symmetry. And numerically, we look at the correlation lengths at different momentums and we precisely find these adjoint representation, the adjoint masses of these two Dirac combs at correct momentum, and they give identical correlation lengths, which seems to suggest this emergent SO3 symmetry. Okay, and also a little bit technical details is how to precisely cut through these Dirac points in a finite size system. By threading flux, we can cut through them, and it serves as a side evidence for these Dirac points. But also it allows us to be very confident that it's truly a continuous transition. Okay, so correlation length truly diverges to 20 or something to be comparable with the system size. Okay. So that's all what I want to talk about today. I think I've been going okay. I'm spend a bit more time than I should, but I should pause for questions.
Yeah, Tiger, thank you for your very interesting talk. Other questions from the audience? Maybe let me ask you a question. You keep saying we should be convinced that this transition is continuous, but have you really ruled out the possibility of pseudo-criticality?
Um, okay, if it's pseudo, okay, I agree. Yeah, it'll be tricky if it's pseudo criticality. Yes, I guess I didn't appreciate it until these recent developments of DQCP. That I agree. That's certainly a possibility. I agree. Um,
Any other questions?
Even
Oh,
if you do DQCP, it seems more first order than this, right? The correlation length. Yeah, you can always, I mean, go between the boundary of how pseudo it is. Um, but it will be a very, very, very ultra weak first order transition if our correlation length is comparable to system size. Yeah,
any other questions? There's a question in the chat.
cool. The operator spectrum. Okay. Unfortunately, this is a beyond approach from this DMRG study. Um, Actually, I think it's beyond any lattice model studies. The way I know how you did it is by fuzzy sphere. It's only when you have this nice state operator correspondence that allows you to read off the spectrum from the spectrum of the system. But usually, when you look at a microscopic model, a lattice model, I mean, the model I've been looking at is in continuum, but it's a lattice model in continuum. It breaks translation symmetry. It doesn't have SO3 symmetry, not SO3 spatial rotation symmetry. Um, so in this case, it's usually very hard to obtain the operator spectrum. The best you can hope is usually a few exponents. If you can measure the order parameter very precisely across the transition, and you can do very nice scaling collapse that may give you a few, I mean, like new, a few lowest scaling dimensions. And from the scaling dimension, we can read off the energy of the few most lowest lying operators, primary operators in your CFT. So that's usually done. And if you want to know more, like more than two levels of your CFT spectrum, you usually have to do something else other than this microscopic model.
So is there any idea to put this on the fuzzy sphere?
Uh, for this, I think it's hard. Yeah, I want to know how to do it. Um, but maybe just give you a glimpse. I don't know if I should do this. This might be a terrible idea. But this is a secret part two of this talk. Oh, this is some generalizations, just to convince you that's interesting. But
Uh,
there's a
yeah, go ahead.
if people like this slide, I can pause. But this is just to say, I mean, where this transition, though this transition itself can be difficult to realize in experiment, because I don't think it has been a pursuit for decades for AMO people to realize the bosonic Laughlin states, but they haven't succeeded. I think there's some very nice progress in recent years, but they haven't succeeded. But you can map that to the CFL to FL transition, which was claimed to have been seen in rhombohedral graphene, um, and also to this CSL to AFM transition, which is claimed to be seen in numerics. So even though it's a boson problem, but by parton and other means, you can transform it into fermionic problem that can be realized in materials. The secret part two is to put this into a larger scope and ask, can you do this on fuzzy sphere? And the complication comes from the fact that it's very difficult to realize a direct dispersion on fuzzy sphere. Naturally, if you do fuzzy sphere regularization, the band will be perfectly flat, okay? Unless you break translation, which is terrible for fuzzy sphere, you cannot get any dispersion. We recently, this is very preliminary, we recently tried to do it by just putting this is a simpler version of this. Just couples the fermions to a critical boson, which is much simpler than the fluctuating gauge field I have been talking about previously. And it gives you a gross normal Yukawa CFT. But the point is, one thing one can try is to put a direct fermion on the sphere. And maybe I should go to the last page. Yeah, these are details about this critical point. Yeah. But one thing one can do, oops, sorry. Ah, sorry, my computer is incredibly slow today. Yeah. One thing one can do is to put your direct operator on a sphere. Okay. Nothing stops you from doing that. You can solve the spectrum of that and then put interactions in the spaces. But the problem is then how do you do a UV cutoff? in fuzzy sphere, it gives you a natural UV cutoff by projecting to the lowest lambda level. But here, the best we can do is to cut off at some finite angular momentum. So this cutoff turns out introducing some non-locality to the system. So it drifts the scaling dimension of a few operators. We're still trying to see if there's a more optimized scheme to do a UV cutoff. But I think this is the first step to do Dirac fermion related CFTs on a sphere. Okay, it's only on the sphere that you can do state operator correspondence and read the entire operator spectrum of the CFT.
Question? Is this
Yes.
omega mu the spin connection or the gauge connection?
This is the spin connection.
So you don't have gauge field at the moment.
No. So as I said, I study a simpler version by coupling the Dirac fermions to critical boson instead of gauge field. That's easier.
Oh, then I see. Then it's so it's still a sphere, but it's not a fuzzy sphere.
It's sphere, but it's not a fuzzy sphere. So we call it a non-fuzzy sphere.
Yeah,
Yeah,
I will
we just
just call it a
couple.
sphere. I will just call it a sphere.
Yeah,
But one thing about simulating fermionic criticality on the fuzzy sphere is that the fermion sees the fuzziness,
that's right.
which we kind of want to avoid.
Exactly. I think that's equivalent to saying when you have a fuzzy sphere, the fermion dispersion is zero.
Mhm.
You don't want the fermion to see the fuzziness. Exactly. That's a
Yeah.
problem. So that's why we tried this. It seemed to work okay. It gives you the CFT towers and everything, but it doesn't seem to give me correct scaling dimension for the current operator, which is my main concern.
Scaling dimension of what operator?
The current operator. Let me just show you the plot. Yeah, it's very slow.
That sounds not good.
Yeah, it's good for sigma, psi, sigma t, but it's not good for J. Also good for T mu nu. Um, there's some CFD argument you can make for why it's bad for J when you introduce non-locality. But maybe a better approach is to try to figure out a way to avoid the non-locality. But that's hard without fuzzy sphere. So we are still trying to improve it. Yeah, but at least the conformal tower looks beautiful.
Thanks. Any other questions? Okay, if not, Tiger, thank you again for the very interesting talk. I will stop the Zoom and we can leave. Thanks.
Yeah, see you soon.
Bye.